Hi, I'm the Amateur Logician, and I want to discuss a not-so-hidden truth about the conditional if P, then Q. And if you really think about it, there's two different versions. We have the common sense or ordinary language version of if P, then Q, and then we have the mathematical or truth functional version you find in propositional logic. They are quite different, and this bugs me a lot because many people do not emphasize this enough, or they don't even discuss it. And in fact, even when thinking about if P then Q, there are several different types of conditionals, such as the subjunctive conditional, the indicative conditional, and that's a huge topic in philosophy. But in any case, think about normal argumentation. When you make the claim if P then Q, there's really an implicit understanding that P and Q have some kind of connection or relation. For example, P might be a cause of Q. So if P is present, then it will cause or bring about Q. But in fact, in mathematical logic, in propositional logic, P and Q don't need to be connected or related in any way, and this goes against the common sense version. That's why I say that the common sense version, strictly speaking, is stricter, and the mathematical version is actually less strict. So, to review, with the common sense version, there's an implicit assumption. P and Q have some real, or that is to say, genuine connection or relation with each other, and P itself, in some real way implies Q. And the most obvious example, P causes Q. For example, let's say if the temperature in this room is 0 degrees Celsius, then the water in it is frozen. Something like that. There's a cause and effect relation there. There's a real connection between P, the antecedent, and Q, the consequent. But let's think more about the mathematical version, which is less strict. Here's an example. If I'm eating ice cream, then Joe Biden is President of the United States. Now clearly P and Q have nothing to do with each other. However, this can be a true conditional in mathematical logic. Nevertheless, we surely wouldn't accept this with a common sense ordinary language version. So this means the common sense ordinary language version is stricter and different than the propositional logic version. And so to review, with the mathematical truth functional version of if P then Q, there is no necessary real connection or relation between P and Q. In fact, P and Q can have no connection or relation whatsoever. For example, with the ice cream and Joe Biden. All that matters are the combinations of truth values of P and Q. That's all that matters. And it's stipulated that if P then Q is logically equivalent to not P or Q. Now, I may have misleadingly in other videos said that in the ordinary language version they're equivalent, but in fact they're not. This statement here is not logically equivalent to the common sense version, although there is a relation, but I don't want to dwell on that right now. However, I want to point out that from this mathematical version of if P then Q, and if we stipulate that if P then Q is logically equivalent to not P or Q, where we can take that or in a inclusive sense, paradoxes result when considering counterfactuals. So let's first do a truth table, and then we'll look at these paradoxes that are quite strange. And so I constructed the truth table, where we have in this column not P or Q, and it has these truth values given the inputs of P and Q. Let's do if P then Q, which must be exactly identical to not P or Q, so this is true, this is false, this is true, this is true. Now what's really weird, ultimately, are these last two results. We call these vacuously true, and it's quite odd. So consider that if the antecedent is false, so here the antecedent is false, here the antecedent is false, anything goes. In fact, all propositions with false antecedents in mathematical logic are said to be true. Here's an example. If elephants are humans, then Mars is a planet. So obviously we have a false antecedent, but we have a true consequent. And also notice that obviously elephants and the planet Mars have nothing to do with each other. So P and Q have no connection, no relation whatsoever, and the antecedent is totally false. The consequent is true, Now in mathematical logic, we'll say this is true, which is really strange. This is a true proposition. It doesn't make much sense, but it is true. It's considered true. If elephants are humans, then Mars is not a planet. In this case, we have a false antecedent and a false consequent. Now in mathematical logic, we're going to call this true. But it's even stranger in a way, because in the first example, we might say we have if P then Q. In the second example, we have if P then parentheses not Q. And from a common language standpoint, there's a sense in which it seems that the antecedent implies Q, and it implies its opposite of non-Q or not Q. And that's really weird, really strange. It is a paradox. So it's really, really important to realize that the common sense ordinary language version and the mathematical truth functional version are not equivalent, they're not the same, and contemporary philosophers do realize this. There's in fact entire books on conditional propositions. They're very complicated and controversial. And there are different moods of conditionals. You have the indicative mood, the subjunctive mood, and there's debate over how you determine some counterfactuals. But in any case, I don't think we should hand wave this problem away. It does exist. The common sense version and the mathematical version are different.